Okay, so for day 3 of fluids, we're talking about hydrostatic pressure. Just to give you what the word means, this is pressure from fluids. If you've ever gone into the pool, gone near the bottom, you feel your ears pop, that's what we're talking about. It's the pressure from the weight of the water itself. Let's go into it. We're talking about how do you figure that out? So let's pretend just for now we have your pool. Beautiful. And here's you near the bottom of your pool. Now let's get a better color. Here's you near the bottom of the pool. You're so happy. Now, if we were to figure out what's the pressure on you, all we would need to do is to calculate what's the force divided by what's the area. All right. What area are we talking about? We're talking about this cross-section area. So let's just, it's a circle, right? If we're just thinking about a smiley face here. So this area right there times the force. The force is going to be the weight of the water above you. Okay. Well, how do you figure out the weight of the water? It's going to be M times G over A. That's all well and good. Well and good. But I can't figure out what the mass is because I can't like measure out this. Well, you say we could calculate the mass. Well, how would we calculate the mass? Because we know that density is equal to mass divided by volume. So we know that mass is going to equal volume times density. And that's what we're going to stick into there. All right, so this brings us another step closer. So we've got volume times density times gravity over area. This is good, but there's something else we got here. The last step has to do with these fellas. Volume is this guy. How much volume is here? Area is this one. But you got to remember that volume is equal to area times height of a prism, of any prism. So volume over area is equal to height. So we have volume over area. So what this is going to turn into at the end of the day, it's going to turn into rho times G times H. And this is the formula that you're going to find almost on your formula sheet. There's something else about it too, but we'll talk about that after a problem practice. So this is the formula for calculating the pressure underwater. So pressure is equal to rho times G times H. Let's think about it. The more dense it is, the more pressure you'll have. Sounds good. That's why water gets more pressure than air because water's a lot heavier. Gravity makes sense. It's pulling down harder. The deeper you go underneath, the more pressure you're going to have. So H is talking about this height, how far underneath the surface you're going to be when we're talking about height. For height of the prism, you could think negative, doesn't matter. Don't worry about that so much. Okay, so this is pressure. Now, although we talked about pressure going down, pressure is going to occur in every direction on this particular depth. All right, so it's going to be pressing this way on the walls, and it's going to be pressing down on top of you. Now it's going to be pressing this way on top of you as well, since we have a curved surface. But we're worried about the magnitude here. It's not a vector, it's a scalar because it goes in all directions at that depth. Let's do a practice problem. So for this practice problem, we have the depth of Lake Mead at the Hoover Dam is 600 feet. I went ahead and switched that over for you. This is going to be 183 meters. What can I say? Except you're welcome. What's the hydrostatic pressure at the base of the dam? So down here, there's going to be a lot of pressure. How much pressure is there? Well, let's figure it out. Pressure is equal to rho times G times H. Density of water, do you remember what it is? It is 1,000. Just one of those numbers that's going to show up all the time. Times G is 9.8 times H is 183. Multiply them all together. So the pressure is going to equal 1.79 times 10 to the 6 That's in pascals, but we don't like that, so we're going to say 1.79 megapascals. Nice. Easy. That makes sense. It's a big number because that is way underwater. You wouldn't want to be in that area without some equipment. Let's keep going to add the next thing, which is total pressure, or it's also called absolute pressure. Okay, so here's the deal. If we talk about that pool that we had a second ago here, right? You're under here, you're having a good time. The problem is the pressure you're receiving is not only from the water, but there's air above the water that's pressing down as well as the water, which is adding on to it. So total pressure is combining those two, and this is the one that's on your formula sheet. So your total pressure is going to equal P0 plus, not M, it's going to equal your rho GH. All right, there we go, there we go. So what this guy is, this is the pressure at the top of the fluid, all right? So in our case, this guy right here, the atmospheric pressure, is going to be the P0. Now you can have this go for multiple stacks. So, you know, if you have one of those little jars with the syrup and the water and the oil and all those other things, you just add all those up together and that will be your total pressure because it just piles up. Okay, so it is additive. So after you do all that together, this guy right here is going to be your absolute pressure. Okay, so let's do some practice. We've got a bucket filled with water to a depth of 1.4. What's the total pressure at the bottom of the bucket? Yeah, some slight modifying there. That's okay. Now, your bucket will look something like this. Choo, choo, choo. Beautiful. It's a big bucket. It's really deep. Anyways, so what's the pressure at the bottom? The pressure is going to equal P0 plus rho GH. Your pressure at the top is the atmosphere. Your atmosphere is pressing down with a 101,300 pascals, right? 101.3 kilopascals. And how it's filled with water? Water has 1,000 times 9.8 times H. H is 1.4. So all we got to do is combine these all together. I'm going to go ahead and switch to kilopascals, which is 115 kPa. Hey, and that's it. Something to notice, maybe it bothers you, the shape of your container does not matter at all. So your bucket could look like this. Your bucket could look like that. Not even going to try. As long as this height is constant. All right? It doesn't matter at all, the shape of it. Now, the reason why is because it goes in all directions. The left and the rights cancel out. It's just the up and the downs and however much you have. Okay. Here's another one. If you want, you can try this one out. Just pause the video. We'll give you a head start here. A pressure gauge measures absolute pressure to be 3.42. Don't worry about this nonsense here. I took out some of the other parts of this because not important. All right, so the air pressure is what it is. Calculate the depth. So what do we have? We have a P is equal to P0 plus rho GH. P, the pressure measured, is going to be 3.42 times 10 to the 5 plus P0, which is 1.013. Whoops, equals 0.013 times 10 to the 5 plus water is 1,000. Now, technically, ocean water is a little more dense. We don't care about that here. It's like 3% different. So you can write 1030 if you really feel like it. I'm not going to bother. Times 9.8 times H. H is what we're looking for. Okay, doing some quick maths here. Our answer, once we figure out what H is going to be, is 24.6 meters. Does that seem reasonable? Yeah, you're at about 3 times atmospheric pressure, so that would be definitely quite a bit underwater. Like the economy. No. All right, one more. This is the fun question. You can try it if you want. For a system in the figure, gauge A reads 350 kilopascals. The pressure in the surface of the water is 180 kilopascals. The height of Mercury, now here's some information for Mercury, SG, do you remember what that stands for? It stands for specific gravity, is 13.3. The height in the tank, the height of Mercury is 1.1. I'm going to write that one in there. 1.1 in there. So write out an expression relating the pressures of the system. So what can I do? So here's what I know. My pressure absolute, my pressure, I'll call it pressure A because it's gauge A, is going to equal the pressure from the mercury plus the pressure from the water plus the pressure from the air, right? Because if I'm here, here's my gauges, I'm getting this much mercury, I'm getting this much water, I'm getting this much air, and then we're all set there. So now I need to calculate this time. Let's change colors. Calculating the height of the water. PA, I know what PA is. PA is 350,000, and that's going to equal the pressure of the mercury. So I'm going to have a rho. The density of the mercury is 13.3 times water, so it's going to be 13,300 because it's really dense. That's why it's so heavy in quotes, times G, which is 9.8, times H, which is 1.1, because we know what that is, plus the height of the water, or the pressure of the water. I know what the density is. It's going to be the same formula, rho GH, times G, which is 9.8, times H. I don't know what H is, but that's what I'm looking for, so I'll be okay. Plus the pressure of the air. I know what that is already. It's going to be 180 kilopascals. So let's throw on the thousands. All right, so all it is we have a couple terms here, and we just got to solve it for H. H is going to equal about 2.7 meters, which seems reasonable given the picture here. Okay, for the last one, we're going to calculate the pressure at point B. So for pressure of B, let's see here, we're at the bottom, basically. Now there's no mercury here, there's just this. So this is actually the easiest one. So this is going to equal your pressure of air plus your pressure of water. Pressure of water. So your pressure of air is going to be the 180,000 plus water is going to be rho, which is 1,000, times G, which is 9.8, times H, which is the whole enchilada here. So it's going to be 2.7 plus 1.1, we'll call it 3.8. All together, what you're going to get is 217 kilopascals. And there it is. Fun problem, ABC. Nice. All right, like and subscribe.